In this video, let's dive into the goodness of fit chi-square formula. We're going to review the formula, its elements, its considerations. Here is the formula right here. So this is the Greek symbol for chi and then squared. Let's see what it's asking us to do. We know that this means sum up everything that's to the right. And what we're going to do is we're going to take the observed frequency for a category. We're going to subtract the expected frequency for a category. We're going to square it and divide it by the expected frequency. We'll do that for each category and then we'll add them all up. That is the chi-square. So in this video, I'm going to be going through some problems using Excel. And right above this video is an Excel practice sheet. I highly recommend that you take it out and practice with it, even if you don't like Excel, because it makes life a lot easier with the chi-square. So here again is a perfect example of a type of analysis that's primed for a chi-square or a non-parametric analysis. The number, this is just a list of the people and then the candidates that they prefer. We can't do any means on this. We can't do any averages on this. This distribution, as I said, can't be normal. It's going to be two different bars on a bar graph, basically. We cannot do any sort of a parametric test. But we still might want to know if one candidate is statistically different from another candidate. In other words, did one candidate get more votes if the election were held today? So we can do something called a chi-square test to figure out if the differences that we're seeing in the counts between candidate A and candidate B are statistically significant. So the chi-square test for goodness of fit lets us know how well our data fits what is expected. The null hypothesis is that our data fits what is expected, and the alternative is that our data is not consistent with what is expected. And so here's an example of a table that we're going to go through. We have candidate A and candidate B, and I have their observed frequencies. That's our data. This is our sample right here. But then what I need to do is set up my expected frequencies. What do I think would be in the population if all things were equal? So we have 10 people in our study, and if there's no preference, then there would be 5 in each group. So that's the expected frequency. To find the expected frequency in this case, just take the n and divide it by, in this case, 2, because there are 2 categories. This is what's expected in the population. What we do for our chi-square first is we take a difference score. We take the observed frequency minus the expected frequency. Then we square that difference score. We're going to take that squared difference score and divide it by the expected frequency. We do that for each category and then add it up. So let's see what this looks like. So we had a squared difference score for category A of 1, and we divide it by the expected frequency of 5. And we do the same for the second. The squared difference score was 1, and we divide it by 5. Remember the rules for adding fractions. If the denominators are the same, it stays the same in the answer, but you do add the numerator. So 1 plus 1 is 2, 2/5, and this gives us a chi-square of 0.4. Now, whether or not 0.4 is going to be statistically significant, we're going to talk about later, but that is the chi-square statistic. Here's another example of how this might work. You might want to know people's favorite ice cream flavor. I know what mine is. So we have 111 people like chocolate, 55 people like vanilla, 44 like strawberry. And so what we do to figure out what would be the expected frequencies is we figure out what the total n is here. So 111 plus 55 plus 44 equals 210. So there are 3 different categories. So all things being equal, 210 divided by 3 is 70. We should have 70 in each category. That would be, if we had all of these people and they were divided equally, it would be 70 in each category. So then what we need to do, as we talked about before, is take the difference score, the observed frequency minus the expected frequency, and then square it. And then what we do then is we divide each of these different squared scores by the expected frequency. And then we add them up to come up with the chi-square. I'm going to do this with you in Excel so you'll get a better sense of it. But you'll notice we have a chi-square of 36.89. It's pretty high, isn't it? All right, let's go to the Excel practice sheet. If you haven't downloaded, I highly recommend that you do so now. As you look at the data sheet, you'll notice that there are 3 different tabs, and that's because we're going to go through 3 different problems. The first tab is for this first problem, which is the goodness of fit when we have a no preference hypothesis. We have candidate A that has 200 votes, candidate B has 240 votes. What we want to know is there a statistically significant difference? In other words, in the population, does this represent a real preference for candidate B? Or is it just that this is random error between these 2 different samples and it really doesn't mean anything? We can figure that out by doing a chi-square test. Here's our formula. I'm going to do this really fast. You can rewind the video and go back. So our expected frequencies, how do we figure this out? Well, it's all things being equal, both groups should have the same amount. So let's figure our total N first. We have 200 plus 240. So in our study, we have 440 total. Now, if we were to take 440 and divvy that up equally, that would be 220 in each group. That's how we come up with our expected frequency. We say that if all things were equal, what would the distribution be of our sample? And then we go through and we follow the directions for the chi-squares. So 200 minus 220 is our first step. So I'll take that 200 minus 220. And then I have to take that number and square it. Then I take that squared deviation and divide it by that. We go back to that expected frequency again. And we end up with a number here of 1.82. We're not done though. Now we do the same for candidate B. We take candidate B's observed frequency minus what we would expect there if all things were equal. We take that deviation and we square it. And spoiler alert, we're doing that so that we don't cancel out the differences when we add them up. We're going to take the deviation and we're going to divide it by the expected frequency. And voila, we ended up with the same because our deviation was the same. So of course, the last thing your chi-square statistic says to do is to add them up. So let's do that. We have 1.82 plus 1.82, and we end up with a chi-square of 3.64. Now, we haven't talked about how to find the critical value yet, so I've just provided it for you here, 3.84. So our chi-square of 3.64 is not greater than 3.84, so we fail to reject the null hypothesis. So what we're saying then is in the population, there really isn't a preference for the candidate, that any difference we're seeing right here between these 2 samples is just sampling error, because our chi-square didn't exceed the critical value. All right, let's keep going. So as a reminder, what we just did was a null preference test. And a null preference, null hypothesis always produces an equal expected frequency because basically we're taking the total number and just dividing it among the categories. So it's always going to be the same when we're just looking at preferences. But sometimes we're looking for a no difference null hypothesis. And in this case, the expected frequencies for the different categories might be different. And so let's take a look at an example of this. Let's say that we have 40 people who take a personality test and they're placed into one of 3 categories based on their score. We had 15 in category A and 19 in B and 6 in category C. Now I want to know if my sample is representative of the known population of personality test scores. Let's say that we know what the percentages are for each category in the population. I want to compare my group to the population. I want to see if my group is weird. So the above categories here are the observed frequencies, and now we need to find out the expected frequencies. We can find out the expected frequencies if we know the percentages in the population. So let's just say that somehow, I don't know how we would know this, but somehow we know that 25% of the population are category A, 50% are B, and 25% are C. When we know those percentages, we can figure out the expected frequencies. So all we do to find the expected frequencies in this no difference hypothesis is we take the total n of our sample, and for each category, we just multiply it by the percentage in the population. So if there's 25% in the population in category A, then 25% of our little sample of 40 should be 10. If there are 50% in category B in the population, then 50% of our little sample of 40 would be 20. This is the expected frequency. And then the same for category C, it would be 10. So that's how we figure out our expected frequencies. We just take the percentages in the population and multiply those by our n for the different categories. So here is an example of what this would look like just applying the chi-square formula. And I'm going to do this fast, but I'm going to show it to you in Excel as well. So we take each score in each category and subtract the expected frequency. So 15 minus 5 gives us, or 15 minus 10 gives us 5, and then we square that amount. So that's what this represents. So we take all these squared deviations. We take each of the squared deviations and divide it by the expected frequency for each group. And then we add all those up to come up with the chi-square. I know I'm talking a lot. Let's actually do it on the Excel sheet. To get to the data for the no difference hypothesis, just click on the bottom middle tab. And here we have some data about the number of accidents people had in a sample. And I want to compare the number of accidents that people had in different age groups to the percent of drivers according to the Department of Motor Vehicles. So according to the Department of Motor Vehicles, 16% of the drivers are under age 20, 28% are between 20 and 29, and 56% are age 30 or older. So I want to see if the number of accidents in each of these age categories is proportionate to the number of drivers in each age category. So this is an example of a no difference hypothesis where we have to figure out the expected frequencies based on these percentages. And so what we need to do is figure out the total n for our study first, which is 300 if you add up 68 plus 92 plus 140. So my expected frequency for the first group is going to be that total n of 300 times the percent that is in the first group, 16 in the population. And my expected frequency for the second group is 300 times 28%, which is the frequency in the second group, or the proportion in the population of the second group. And the third one is 300 times 56%. All right, that's how we get our expected frequencies, that we have 68 accidents, so we would expect there to be 48 if it's proportionate to the population. We had 92 accidents here, we would expect it to be 84, etc. So now we're going to do the chi-square to see if these differences that we're seeing between our particular sample and the population, if it means something or if it's just random error. So the first thing I do is take the observed frequency in the first category minus the expected frequency. And then I take that deviation and I square it. And then I take that squared deviation and divide it by the expected frequency for this particular category. I do the same for the second. I'm going to take the observed frequency minus the expected frequency. I'm going to take that deviation and I'll square it. And I will take that squared deviation and divide it by the expected frequency for that group. And I'll do the same for the last group too. Observed minus expected. Take that amount and square it. And then take that squared amount and divide it by the expected frequency for that group. Now I have three different numbers that I need to add together, because if you look at the formula, we did all this fancy stuff here, but now we have to add them to come up with the chi-square statistic. So So I'm going to take 8.33 plus 0.76 plus this last one, and I end up with a chi-square of 13.76. Now, as a reminder, we haven't really talked about significance yet, but I will tell you that the critical value, if we're doing alpha at 0.05, is 5.99. So this is way past 5.99. So what I'm going to say is there's something different about my group. In other words, the number of accidents people are having does not match up with the breakdown for the population of just regular drivers. Something's going on here. All right. So our expected frequencies define the ideal and the hypothetical distribution. And because they are hypothetical or ideal, they might be decimals or fractions. It's very possible. But our observed frequencies, you might have already noticed, always represent real individuals, and therefore they're always whole countable numbers. In the next video, we're going to talk about how do you make decisions? How do you figure out statistical significance?